Another example of greedy design technique called coding problem. Suppose we have to encode a text that comprises symbol from some n symbol alphabet by assigning to each of the text symbols some sequence of bit called code word. In that we have a some alphabet made up of the word, and we try to convert into certain code word, which is actually convert the word into certain code. For example, we can use a fixed length encoding that assign to each symbol a big string of the same length, m greater than equal to log n base 2. This is exactly what the standard ASCII code. The idea is try to convert the alphabet to the certain bit or binary. So coding, what is coding? Assignment of big string to alphabet character. So we assign the word into certain bit string. Code word, a bit string assigned for a character of alphabet. Two type of code, fixed length encoding, example ASCII code, and variable length encoding. The algorithm, for example, we have a Huffman code and Morse code. So now we look at on the Huffman code as example for the coding problem here. So what is a Huffman code? Any binary tree with edges labeled with zeros and 1 yield a free code of character assigned to its leaf. So Huffman code using the binary 0 and 1, and before that to yield the 0, 1, we have to construct the binary tree to represent this. Optimal binary tree minimizing the expected weighted average length of a code word can be constructed as follows. This is the algorithm. So I think we skip this. We go to this. Let's say we have the example. This is a character. We have A, B, C, D, and underscore here. And let's say we have the frequency we need to assign. The given already the frequency for the A is 0.35. For the B is 0.1 here. For the C is 0.2, D is 0.2, and the underscore 0.1. The frequency here is when we sum all this, we get 1 here because the frequency. Okay, the step 1 for the Huffman code. Initialize and one node tree with alphabet character and the tree weight with their frequency. So this is actually the frequency given to us just now. A is equal to 0.35, B equal to 0.1, C equal to 0.2, D equal to 0.2, and underscore 0.15. For example here. And we need to rearrange them in increasing order based on the frequency here. So this is the first one, the second one, the third one, the fourth one, and the fifth one. So we have to arrange, and finally we need to construct the tree based on the pair of this frequency. Okay. The next is repeat the following step n minus 1 time. Join two binary tree with smallest weight into one as left right subtree and weight equal to sum of the weight of the two trees here. So we have to combine this. When we sort here, this actually the first minimum group here, the pair 0 1 here, and the second here, and this there's no pair here, we remain a single here, and finally we have to obtain this 3 here with sum of this 0 1 1.0.5, which is 0.25, for this 0.4 and 0.35. Okay, next is rearrange them in increasing order. So we have to rearrange. This is actually the minimum. These are greater than 0.5, actually greater than 0.4. So we arrange like this. And net join two binary tree with smallest weight into one left and right subtree. So we have to join this because when we arrange this 0.5, 0.25, this is actually the highest. And net we have to get the pair of this to join the tree, become like this. So now we have this tree with joining B and underscore, where we get the frequency, the sum of 0.25, and after that we have to add with 0.25 and we get 0.6, and finally we have 0.4 here, and finally we need to rearrange 0 here sort 0.5, 0.6, and combine in order to get the sum is 0.1 here with this sub 3, is a sub 3, and finally the step 3 mark edges leading to left and right sub 3 with zeros and 1. So the left is 0, the right is 1, so we get this 0, the left 1, this 0, the right 1, the right 1. And next is to assign the code word here. So for the A just now, so this is the, these are for the A here, we say A here, based on the arrangement just now, new arrangement, 1, 1. So we obtain the code word is 1, 1. For the B is here, 1, 0, 0. That's why we obtain 1, 0, 0. For the C here, which is C here, 0, 0. For the D is 0, 1. And finally, for the underscore is 101, this code word. So we convert from the alphabet here, A, B, C, D, into a code using the binary representation, where we convert the code A into A into A11, B 100, C 00, D is 01, and underscore is 101. Okay, Huffman code is a function from just now frequency, convert in this code, and average bit per character is 2.25, where it is 2 times 0, this is frequency, 3 times 0.1, 2.02, which is value 2 here. Finally, this is actually the average bit per character. For fixed length encoding 3, so the maximum is 3 because these are the 3, 100 and 101. Compression ratio is 3 minus 2.25 divided by 3 because of fixed length 3 times 100%. So in terms of compression ratio, we can use to 25%. So this Huffman code, basically in application we have two. Number one, actually to encrypt the code, mean from the convert from the alphabet to the code word as a coding, and number two is for the compressions of the file.